Hello, everybody. My name is Jake Rupp, and today I'd like to talk to you about intercooling jet engines. First, let's talk about how this technology can be applied. Since the end of World War II, jet travel has become one of the primary modes of international transport, and its use has skyrocketed over the past like 6 decades. Um, it's now the mainstay of the aviation industry, um, and more people travel by jet than by any other form of aerial propulsion, such as propellers. Over the years, many different technologies have been developed um, in order to make jet travel more efficient and faster. These include airflow bypasses, like high bypass turbofans used on virtually all airliners today, variable geometry nozzles, mostly for supersonic aircraft such as the Concorde, as well as most fighters, and geared turbofans and twin spool and triple spool radial compressors that are used to increase the efficiency of the compression of air before ignition. The objective of this project is to design an intercooler that can further advance the technological innovations made earlier, and make jet travel more efficient and produce engine that can make a difference on thrust using the same amount of fuel. This will be tested predominantly using the ANSYS Fluent software and analyzed to decide whether there's a significant effect, and whether that effect is worthwhile and applicable to the aviation industry. There are some key benefits that come out of using intercoolers, and these are the benefits that I will weigh with its cons as well. This is increased available power, increased fuel efficiency, and faster throttle response. And those are three things that we're going to go over now. If you now pay attention to the middle column of the poster, I'd like to talk about what an intercooler is and how it works. So, in the four cycles of a combustion engine, we can, any pretty much any combustion engine, we can kind of narrow it down to four main parts of the cycle. There's intake, where air enters the system; compression, where air is compressed. In a car, that can be with the piston in the compression cycle moving up and closing the cylinder, or in a gas turbine such as a jet engine, the radial or centrifugal compressor that compresses the air. It's followed by ignition, where air is mixed with the compressed air is mixed with fuel and then ignited, and then exhaust, where that air fuel mixture that's been burnt leaves the system, providing thrust and power. Now, in between compression and ignition, we can use intercooling, where hot air, because after compression, the air heats up. After compression, that hot air runs through a compressor, which is cool, which through two veins is in one direction is that hot air coming from the compressor, and the other is the relative wind, and acts as a heat exchanger and allows the hot air to cool, with two side effects. One, it's denser because cold air is denser, which increases the overall compression ratio, and it also increases the thermal efficiency by keeping that air cooler. It'll then travel to the combustion chambers for ignition. Now, if you would pay attention to the bottom of this little bar at the bottom over here, intercoolers are nothing new. In fact, they're already used for several purposes. They're used in mining, power, heavy industry mostly, to increase the efficiency of gas turbines. So yes, a jet engine is actually a gas turbine, but the gas turbines are used in two very different ways. In a jet engine, the gas turbine is used to push air out of the exhaust. However, in most of these heavy industry applications, the gas turbine is used to turn a turbine and use that as rotational force. It's used to increase the efficiency of those. It's also used in the automotive industry for particularly for high performance cars. Um, Picture it as a Subaru WRX STI, which has an extremely high uh, boost level coming from turbochargers. And turbochargers are essentially centrifugal compressors, which were actually seen on earlier jet engines. And basically, they do cool the air and do exactly what they do for the other two applications, and it cools the air before it enters the cylinders for ignition. Um, Above, or actually below, I kind of laid out my research plan in a very basic manner. And my first step is to design a basic intercooler and get familiar with the ANSYS Fluent software. If above right here is the basic intercooler that I've designed, and each of the vanes is 1 inch apart and 5 inches by 5 inches, and that's obviously not what the actual application of an intercooler would be like. That would be more like the rendition by Xin Zhao of the Commerce Institute of Technology. That is a much more practical implementation of an intercooler design for a jet. Um, and But this is a start, and it's more as a teaching tool for myself, so I can learn how intercoolers work and heat exchangers work, and get more familiar with the ANSYS software. After that, my next step is to test the basic intercooler using the ANSYS Fluent software. Um, and that will just kind of again teach me how the intercooler system and ANSYS system works. After that, my goal is to design a usable intercooler for a jet engine, and an intercooler that, like the one drawn up by Xinjiao, is more applicable to the industry and will be more realistic in terms of its performance. Um, After that, the next obvious step would be to test that intercooler using the same software and the same techniques in which I used for the basic intercooler, and then develop data and further review how all of that culminating evidence can and decide whether it is practical and worthwhile for the aviation industry too. This large picture right here is another one of Zinzao's rendition of how the intercooling system could be implemented using um, a small secondary bypass within the larger bypass after the turbofan, and use the relative wind from that bypass to cool the air. Now, I'd like to talk about the opportunities and setbacks I've had while using this project. One of the probably the largest opportunity I've had is being able to pursue this project in general. The program has definitely taught me a lot of things, and I definitely would not have been able to pursue my interests in this fashion anywhere else. Another opportunity I've had is having access to CAD and fluid testing software, which I would not normally have had. Um, that software is extremely expensive and hard to come by and difficult to use, but because I'm a student and I have the available resources, I can access tutorials as well as the software. Um, However, I've also had many challenges, and I think one of the biggest ones was finding out how to test my idea and coming down to something workable. Because at the beginning, I had these huge plans, and I wanted to build an actual jet engine And then as time went on, I realized that that would not be possible given the environment and situation, its impracticality, and also like finding out how to test it. I have very little background in, actually, I have no background in fluid dynamics or ANSYS, or really this whole thing opened my eyes to the world of aerospace engineering, and then that brought on that next challenge, which is learning about fluid dynamics, which was, as I found out, a bit uh, very challenging, and I commend everyone who works in that field. And lastly, looking forward, there are many ways that we can continue this project and get an idea of whether or not, and answer the true question, whether or not it will be applicable. And as of now, as you can see, this project is mostly in the digital and researching realm. However, if physical testing were to ensue, uh, you would get a much more realistic and material result that would be much more applicable and visible to the industry. Um, Seeing if you observe the intercoolers change on a jet engine, it will surely be different from the ideal testing, as well as the not as complete testing in terms of variables. In when you test a physical model, every single variable that comes into contact with that intercooler can pretty much be tested. Um, Whereas in ANSYS, it's conducted on a very ideal basis. Um, and then that would kind of, taking into account those inefficiencies that would come, it would yield a more accurate picture of whether the intercooling is actually practical. Um, it also could look at, shed light on some other important issues that could come with it, such as structural issues, performance issues. How much drag does it cause? Does it like, is it more problematic than it is beneficial? Um, and then after initial stationary testing, you could also look at wind tunnel and hush house testing to determine whether how intercooled engines operate at a variety of speeds. And when they operate at a variety of speeds, that more than anything will give the aviation industry a good picture whether intercooling will be a technology that they could see in the future. Thank you.